Today, başlayalım Ömer. Today we'll be talking about space and celestial objects. It's a mind-blowing topic because yesterday I was also having my class for the engineering students. At the end of my class, I asked if they have any questions, and they sit back, and I had some questions from the space, like black holes and so on and stuff. And tonight, we are having our guest from European Space Agency, Dr. François Mernierye. Thank you for him accepting our invitation. I want to make a short introduction for François. After graduation from Belgium, he had his PhD in Leiden University at High Energy Astrophysics in Esron, which is a very outstanding leading institute in the world in this field. And following his PhD, he conducted postdoctoral research again at Leiden and MTA at WOS University in Hungary. Excuse my pronunciation if it's wrong, at WOS. And currently now he's a research and he's a research fellow at the ESA, European Space Agency in Estek, the Netherlands. His research mostly focuses on the X-ray observation of the galaxies, galaxy clusters and groups, and massive objects. He also interested in the use of metals as passive tracers of the gas dynamics triggered by the supernova black hole activity and the effects of gas cooling, which we'll be hearing the details in his presentation. Dr. Manier aims to explore the coupling between these two intriguing aspects from galaxy to the large scales. Now he is interested with the future X-ray observations, in particularly the Athena mission. So I guess that's a brief introduction is enough. Okay, François, we are listening. Your presentation. Thank you.
Yes, thank you very much, Murat. Good afternoon, everyone. It's a real pleasure to be here. Well, not physically, of course, but still to be able to give you this presentation, which I named the link between supernovae, supermassive black holes, and the large-scale universe. So we're going to see a little bit what this link is, but I would like actually already to give you a huge spoiler alert and already tell you what this link is, because that's going to be central for the rest of the talk. So this link is actually what we call metals. So metals in astronomy, which are all these chemical elements which are heavier than hydrogen and helium. So, namely carbon, oxygen, iron, etc. So all these metals that we are also made of. But we're going to go a bit into these details. So as a quick outline, I still would like to devote a lot of time for a nice introduction, because I think it's quite important to tell you more about the topic, what we know today. And then the second part will be a bit about the work we've been doing with our collaborators across Europe. So this is mainly on the chair samples. I will explain you a little bit all this, and also why we have these 3 or even 4 points here. Eventually, I will just spend a little time on future missions, and then I will just conclude. All right, so let's first start with an introduction. So when I tell you about chemical elements, one of the biggest questions asked from me is basically, where do these chemical elements come from? And part of the answer actually resides in what we call, of course, the Big Bang. So the Big Bang, which is this very big expansion of the universe at its very, very beginning. And what we know is that a few minutes after the Big Bang, atoms started to be created. And we know that basically almost all the hydrogen and helium of our universe was created during this primordial nucleosynthesis here. So we have basically 75% of hydrogen, 25% of helium. We have a little bit of lithium as well, but something very, very small here compared to hydrogen and helium. So we can actually wonder, how about all the other heavier elements that we know, what we actually call metals in astrophysics. So, as I told you, carbon, oxygen, etc., etc. Well, the answer here is actually mind-blowing, just that they all come from stars and in particular supernovae. So here it's important to distinguish at least two different categories of stellar objects, and we'll first start with core collapse supernovae. So core collapse supernovae are basically all these supernovae you can naturally think of, which are just like when massive stars, so stars which are more than 10 times the mass of our sun, arrive at the end of their lives. And what happens is that when the stars produce too much, start to produce a bit too much hydrogen and then helium, the temperature in the core will increase, and you will have burning of heavier and heavier elements, and you will really have this onion-like structure here with element burning up to iron. So iron is really in the core. And what happens after iron is that you can't create more energy by transforming or burning, let's say, silicon into iron or iron into heavier elements. And so basically iron will stay in the core. And then at some point you will have a lack of balance between the gravity of the star and the external pressure. And so the gravity will basically win and will just completely collapse onto the core. The external layers will bounce against this iron core and will be violently ejected outside of star. So the star will die, and you will have what we call core collapse supernova. So as I told you, this happens for massive stars, and massive stars they live very, very fast actually. So they live only a few million years, so which is basically nothing for the scale of astronomical scales. So what's also interesting is that this core collapse supernovae produce not all heavy elements, but a specific one. So in particular, oxygen, neon, magnesium, and silicon. So what I would call here the light metals. And we can also ask how much of these metals are produced in proportion. And this depends on two things. This depends on the mass of the star. And so if I don't talk about one star, but if I talk about an entire population of stars, I can talk about the initial mass function. So basically the distribution of masses on this entire population. And it also depends on the initial metallicity of the star. So whether the star already contains metals, so heavier elements when it was formed. So I'm just going to give you an example here on this plot. So here you see different nucleosynthesis models from the literature. And each of them has different either mass or initial metallicity. So you can see here initial metallicity of 0, 0.004. So the more the initial metallicity, the more metals the stars contain before. And you can see that when they explode a supernova, models tells us that they basically produce elements in different proportions. So again, you see like a lot of oxygen compared to almost no iron or nickel, but a lot of oxygen, neon, magnesium, but in different proportion, which is kind of useful because if we can look at one core collapse supernova, for example, if we can measure here the oxygen over iron ratio, which is these plots, then you can say something about its initial metallicity or its initial mass, etc. The second channel of creation of metals in the universe is actually type 1a supernovae. So these are another type of supernovae which are kind of different actually because they don't come from massive stars, they come from low mass stars. So we don't exactly know what happens, but we know that when a low mass star dies, it dies into what we call a white dwarf, which is a very, very dense and compact object. And either this white dwarf collides with another white dwarf, which will just generate a huge explosion, or this white dwarf will basically accrete the material from a companion star, and this will basically trigger an increase of temperature, actually, which will not be able to be balanced by the white dwarf. So at some point you will have this huge explosion, and this explosion will produce metals as well. But this will produce heavier metals, so typically from silicon, sulfur, argon to iron and nickel. And something else that we can say is that of course, in type 1a supernovae, since we talk about low mass stars, actually low mass stars take much longer time scales. So they live much older than high mass stars. So because of that, you have a long time delay between star formation of these low mass stars and these type 1a explosions. So how much of these metals are produced? Well, here again, it depends on a few parameters. And the parameters are either the physics of the explosion. So either the burning flame in the explosion can always propagate subsonically. That's what we call a deflagration. Or at some point, this burning flame can reach supersonic velocities. And then that's what we call delay detonation explosion. So I will show you in a few minutes what's the differences in terms of metals. It also, the nature of the progenitor can also change the ratio. So today we still don't really know whether this, which scenario is actually the good one for type 1a supernovae. So either this one, which is called double degenerate scenario. So when you have type 1a, white dwarf just colliding, or single degenerate scenario, which is when you have this slow accretion from a main sequence companion. And actually, you can also do exactly the same exercise as before. You can just take all these models from the literature that I all put here with respect to iron, which is one here. And so you can see that, for example, if I look at the nickel over iron ratio, some models, especially these ones, which are actually deflagration models, will give me more nickel over iron ratio than the blue ones here, which are, for example, delayed detonation models. So what I mean by this is that, again, we can just look at one type 1a remnants in our galaxy, for example, and if we're able to constrain the abundances, then we will be able to say something about how this supernovae has exploded, which is very, very interesting and very important to really understand these objects. There are a few other channels which I'm not going to mention too much here. So the first one is the third one actually is the asymptotic giant branch star, which are these intermediate mass stars which just arrive at the end of their lives. And what happens is that they have a convective envelope in which a lot of nitrogen and carbon is created, and via heavy winds, these materials will just propagate outside of the star. And finally, you may have heard about this beautiful discovery, I think 4 years ago from now, from LIGO, showing that actually you have merging neutron stars were detected through gravitational waves. And these merging neutron stars are actually responsible for the creation of very heavy elements. So for example, gold, silver, etc., etc. But I'm not going to mention that here. So this is basically just a summary of the origin of chemical elements. And you probably all know this beautiful quote from Carl Sagan that we are all made of star stuff. So oxygen, for example, that we breathe, which come actually from core collapse supernovae, iron, which is in our blood, that really comes from type 1a supernovae. So all these elements were once created in this burning cores of stars or supernovae, which I find beautiful. All right, now let's completely move the topic. Let's zoom out and let's look at the universe at its larger scales. And this is what it looks like. So here you have what we call a galaxy cluster. So just a lot of galaxies everywhere, which are just attracted by each other because of gravity and because of dark matter, which is also a manifestation of strong gravity. And this is what it looks like when you take it with optical light, when you look with, I would say, a normal telescope. But of course, you have a lot of other wavelengths that our eye cannot see, but that also exist in the universe. And one of them is X-rays. And if you look at these galaxy clusters in X-ray, this is, I will come back to that a bit later. This is basically what you see. So you don't really see any, you don't really see the galaxies, the individual galaxies anymore, but you see like a very, very blurred and diffuse emission here. And this emission, well, I think about 45 years ago, astronomers understood what this very blurred and diffuse emission was about. And this was actually about a very hot gas. So when I say a gas, the temperature here is so hot that the electrons are not even bound to the atoms anymore. So this is more like a plasma, actually, I would say. So this is what we call the intracluster medium. And this intracluster medium is hot, it's very tenuous. It's also optically thin. So each photon really corresponds from where you sit. So you don't really have interaction with matter, which is quite convenient. It's also in what we call collisional ionization equilibrium. So the rate of ionization is equivalent to the rate of recombination. So the gas doesn't become more and more ionized or less and less ionized with time. And finally, this gas is very important because it accounts for 80% of the total baryonic matter in this cluster. So just imagine that you take all the stars, all the planets of these galaxies all together. This is not even 20-25% of all the matter. And this matter is actually really in form of a gas. Something that I also wanted to come back here. Yes, it's also that if you look at these galaxy clusters, what you see first you see that these galaxies are what we call red and dead. So they are not really like our Milky Way. They're not really blue with beautiful blue massive stars, but they actually contain a lot of low mass stars, quite old stars actually. And you also see that in the center of these clusters, sometimes, not always, but sometimes you have what we call brightest cluster galaxies. So one galaxy which is actually much bigger than the others because it has basically eaten the other galaxies. All right, these are just some other images that I really like, showing again this intracluster medium or these hot atmospheres you have around clusters and galaxy groups. And what I want to show here is that, yeah, this happens for cluster, but also like for galaxy groups, which are basically lower mass scales versions of clusters. And also you can see this hot gas surrounding individual galaxies as well. So this is the case here for NGC 1404, but this is another example of NGC 5813, where you have this hot halo, which is just around this galaxy. So you really have this at many scales. Something I would like to introduce is that we make a distinction between what we call cool core clusters and non-cool core clusters. So the difference is just that if you have a very relaxed cluster where nothing really specific happens, then the core will really cool down. It will just emit a lot of this X-ray light, and the temperature will be quite cool in the core. And it's basically in this cool core cluster that you have this big BCG, so brightest cluster galaxy. If you have like a cluster that has recently merged, for example, or with a lot of gas interaction, you won't really have this central cooling. You will have a much flatter temperature. So that's what we call non-cool core cluster. I will come back to that in a few minutes. And something that's extraordinary, at least in my opinion, is that this intracluster medium is not made of only hydrogen and helium, so not only primordial gas, but it also contains a lot of metals. And that's here that we're going to make the link between this type 1a and core collapse supernovae, as I introduced before. So here is basically a spectrum. This is one of the first spectrum of the Perseus cluster, where you can see a bump here at 6 keV. And this bump at 6 keV corresponds to the emission line of iron, which re-emits at this line. So again, it means that this intracluster medium contains metals. And it doesn't contain only iron, actually. If you look now with modern X-ray observatories, and this is an example, this is XMM Newton, you will see actually a lot of other emission lines. So you will see here oxygen, magnesium, silicon, etc. Here again, the beautiful iron line, nickel as well, etc. So this doesn't seem very convincing if you look at this spectrum, simply because you have a lot of continuum. But if you actually subtract the continuum and if you stack a lot of this data, you will find something like this. And here you can see these lines much better. And again, each of these lines correspond to some metals that were basically released in the intracluster medium. And these metals correspond to a lot of explosions from either type 1a supernovae or core collapse or both. If you basically look at this part of the spectrum here, you can see that this complex here is not really resolved. It actually contains a lot of lines. It's just because our spectrometers are not do not have yet the spectral resolution to resolve these lines. However, we have another instrument on board XM Newton, which is the RGS instrument. And you can see these lines in this iron L complex better. So you can see oxygen, for example, here, magnesium, etc. And finally, there was also a mission that was launched in 2016, so in a few years from now. Unfortunately, the lifetime was very, very short, but this mission still managed to look at the spectrum of one cluster, so the Perseus cluster, with exquisite spectral resolution, because this instrument had microcalorimeters on board. And here you can see the same sort of spectrum, but with very, very thin lines, very well resolved. And that was quite impressive, actually. You can see here the comparison of this new spectrum from Hitomi in black versus in red, what you could see from XMM Newton EPIC camera, so the one I showed you before. All right, so if I just go back to this very nice periodic table, I would basically add something. I would just add that, well, we are all made of star stuff, but surprisingly and amazingly, I would say this star stuff is not only present here on Earth or not only around stars, it's present at the largest scales of the universe. So even outside, very far away from galaxies, you still find these metals. And this is something that we would like to understand here. So in this talk, I'm going to focus specifically on metals from oxygen to nickel, because these are the metals whose lines actually peak in the X-ray band so that we can really detect with X-rays. So yes, basically what we want to understand now is, well, a few questions, but of course it's where, when, and how did these large-scale structures become chemically enriched? How did that happen that we find all these metals so far away from galaxies and everywhere in the volume of these galaxy clusters? And there are a few things you can do to do that, and I'm going to discuss that in a few moments. Of course, if you want to tackle the when, you can look at the redshift evolution, but I'm going to show you that this is a bit complicated and that we can do easier things actually. And one of the things I'm going to focus on is to look at the abundance ratios in nearby clusters, and also in nearby clusters we can look at the spatial distribution. We can also look at the comparison between clusters and groups. But let's discuss that very soon. So something else I want to introduce here is the concept of what we call R500 or R200, which is just this radius within which the density of the gas is 500 or 200 times the critical density of the universe. So this is just a way to measure the typical size of a cluster. And we like to distinguish what we see in the core of the clusters versus what we see in the outskirts. So I'm going to discuss that in the next slides. All right, so I will first start with the spatial distribution of metals in galaxy clusters. And this is typically the sort of shape that we find here and that I'm going to discuss now. So first, let's look at what happens in the outskirts, so outside of the core. Outside of the core, what you see is that, well, of course, you have these metals just decreasing, but they don't decrease to zero, actually. There's always some metals even very, very, very far away from the cluster, even in gas regions which has not yet virialized and been incorporated into the cluster. You really see here a remarkable uniform level of metals, which is around 0.3 more or less. And this is extremely important to see because actually simulations will tell us how to interpret this. And this is what you can see here, where you have two simulations, one with supermassive black holes feedback and one without supermassive black holes feedback. And so what the simulations tell us, the way we can interpret these observations, is that all these metals were actually enriched outside of galaxies, were really ejected outside of galaxies before clusters started to assemble and before even this gas started to be created. So we talk here about the redshift 2 or 3. And so according to simulation, this has to happen mostly via AGN feedback. So in other words, supermassive black holes in the center of galaxies really helps to push all the metals out of these galaxies, to mix these metals uniformly around galaxies at very, very large scales. And then only then galaxies started to assemble into clusters. All right. Yes, so something else. Now we can look in the core And what we find in the core is that we find this central increase. This increase is actually found mostly in what we call relaxed clusters, so these cool core clusters. If you look at non-cool core clusters, you will have a peak that is a bit less constrained. And as I told you, in cool core clusters, you usually have this brightest galaxy, cluster galaxy here, so this big galaxy. And so back then, it kind of made sense to have this, because if you have a lot of low mass stars in these galaxies, here in the center, you will probably have a lot of type 1a explosions. And if you have a lot of type 1a explosions, you will probably have a lot of iron that is just building up here. And so that's what we believe happened. At least that was the initial interpretation. I'm going to show you later that this is a little bit more complicated than that. All right, that was my very long introduction. Now I will just discuss a little bit about what we did recently. So most of this work is based on what we call the chair sample. So the chair sample is just, I'm not going to go too much into details here, but it's just a sample of galaxy clusters, groups, and ellipticals seen with XMM Newton and seen with very good accuracy. So usually very deep observations of clusters, groups, and ellipticals. And so this is about 44 systems in total. And in total, we have 4.5 megaseconds of total exposure. So if you're familiar with X-rays, you realize this is quite a lot. All right. And so the strategy behind it is just to have, well, this is typically what a cluster looks like on your X-ray detector. So where you have the hot gas all around here. And with the EPIC camera, you can basically look at any region of your choice. Of course, you need to be careful about the background, etc. But you can do that. And for RGS, you don't have choice. You can just look at the central part here. And what happens is that if you take, and let's first focus on EPIC, if you just take one spectrum here, let's say 0.2 R500 here, then you will have this spectrum here, and the data are shown in black. And then you will basically fit this data with models, so spectral models coming from actually spectral codes. And once you have your best fit, you can basically optimize your parameters and, for example, get a best fit of abundance or temperature, etc. So that's basically how we can derive abundances in this hot gas of galaxy clusters. All right, so one key result here is if we focus on central iron abundance in cool core systems. And here the motivation behind it is just that typically, to form clusters, you have to form them what we call hierarchically. So you have to form them first from galaxies, then from groups, and then eventually they're assembled into clusters. And so that's why we wanted to look at the chemical contents of all these systems and compare them to see whether groups are more or less enriched than clusters and so on. And from the previous literature, this is typically what we find. So this is a plot of iron abundance here on the y-axis versus temperature on the x-axis. And the temperature is actually a good proxy for the mass of the system, in the sense that hot systems are usually hot clusters that are usually massive clusters, while on the other hand here, cool systems are usually poor galaxy groups or even individual elliptical galaxies. And what you can see is that actually there's a sort of trend of, well, more or less stable abundances here for massive clusters. But if you go for cooler and cooler systems, so basically less and less massive systems, you see less iron abundance. At least that's what previous observation showed. And the problem is that this is conflicting with simulations, actually, with what you would predict theoretically, because in theory, you would predict to have as much iron in groups and ellipticals as you would have in clusters, and that's not what you observe. And what we did recently is that there was a big update in this spectral code, which I'm using, which is called SPECS. So it went from version 2 to version 3. I won't go in too much into details, but the difference is that a lot of spectral lines were better calculated and incorporated in this code. And if you do the same sort of plot for chair sample, and if you do also this temperature, so basically mass versus central iron diagram, you can measure it for SPECS 2 and SPECS 3, then you will start to see a difference. And what we basically discovered that when you use the new code, which is more realistic, then unlike before, now you find something that's on average very consistent between clusters and groups and ellipticals. So yeah, for the first time, you could really find this similar central iron abundances here, which you can also find here with histograms between the two, so SPECS 2 and SPECS 3. And good news, as expected, this is also better. This is better consistent with tailored simulations here, as you can see in the red envelope there. All right, so I'm going to discuss a bit the implications of that a bit later. Now let's look at something else. Let's look at not only iron, but all the other elements. So what we call the chemical composition of the intracluster medium. And so this plot shows you like all the average abundance ratios. So oxygen over iron, neon over iron, magnesium over iron. So iron is here normalized to 1. And so in other words, this shows you basically the chemical composition of the intracluster medium. And we may wonder, well, why is it useful to look at all these elements and all these ratios? Well, this is useful because if you remember what I said in the introduction, if you just look at one core collapse supernova or one type 1a supernova, if you can constrain the ratios of their explosions quite well, then you will be able to constrain the physics, the stellar physics that you have behind. So for example, the initial metallicity of core collapse supernovae, or the explosion of type 1a supernovae, or the progenitors of type 1a supernovae. And here it's actually even better because we don't talk about 1 or 2 or 3 type 1a or core collapse. We talk about millions and billions of them that have just exploded and that have completely enriched the intracluster medium. So what we can do here is that we can just take, randomly, for example, one core collapse model plus one type 1a model and fit our observations or observed ratios with this model. And we can try that for a lot of combinations of models and try to see which ones will fit this shape better. And so that's what we can do here. And I'm just showing you for this specific example, the best fit that we find. So we see that our observations favor, for example, a core collapse model with initial metallicity of 0.01, which is not 0, but it's still quite low. And it favors also like type 1a models, which is a delayed detonation model here. And as free parameter, you can say that the fraction of type 1a over the total number of supernovae in the nearby universe, or at least in galaxy clusters, is about, let's say, 40%, more or less. Well, this is not exactly true, to be honest, because this exercise was done quite some time ago, and that was done with SPECS version 2. And as I told you, SPECS version 2 gives quite different results from SPECS version 3. What happened also in the recent years is that, well, here I just show you the exact same plot as in my last slide, but there has been some improvements, not only on spectral codes, but also on the space mission, because I told you about this beautiful Hitomi mission that was there in 2016. And Hitomi could really measure with this beautiful spectral resolution, it could reconstrain the abundances of all these elements here. So from silicon to silicon over iron to nickel over iron. And you can see that everything is really consistent with 1. These results were also made with the new version of SPECS. And they're actually, they go quite well with like another very, very nice results here. Again, for Hitomi and SPECS version 3, but also completing here what you have in the for oxygen, neon, and magnesium over iron. And so when we saw that, we were quite motivated by just looking back at our old XMM data, but refit all of them with a new spectral code with SPECS version 3. And if we do that, what we find is something that, again, is very consistent with what Hitomi has found, which is also really reassuring. And overall, the most important here is that if you look, all these abundances are remarkably consistent with the proto-solar value, or the solar value here, which is basically 1 for reference. So this is actually very, very important. It basically means that all these abundance ratios are consistent with solar. So in other words, the chemical composition of this hot intracluster gas is remarkably similar to the chemical composition of our own solar system here. I'm going to come back to that in a few minutes. Another plot I would like to show you is this one. So this one comes from that previous study I showed you, so by Siminescu et al., showing here mostly the Hitomi measurement. And this is a bit of a better plot comparing all these type 1a and core collapse models. So this is a bit more recent. And something that you can also see is that it's kind of sad to say, but actually none of the current combination of models is able to reproduce all ratios at once. So you see that, for example, it's very difficult to have both sulfur and argon at once here. So what does this mean? That then maybe nucleosynthesis models needs to have more, to be more realistic, to have more improvements to really fit these observations better. All right, so I just showed you this plot before, if you remember. So this is just a temperature versus iron abundance plot. Now we can do the same. We can compare groups and ellipticals versus cluster, but this time for the abundance ratios to see whether the chemical composition will be different from groups and ellipticals to clusters or not. And what we find is that indeed, there's really no difference, at least no notable difference of chemical composition between groups and clusters. So it's not only about iron, it's about all the other elements as well. All right, there's a third point, which is now we can start to look at the spatial distribution of not only iron, but all the other elements. And that basically means the distribution of type 1a versus core collapse enrichment. So this plot, I haven't shown it to you before, but this is very similar to the plots I showed you with a spatial distribution of iron. So if you remember, we have a central peak, and then here further away, it just stabilized to a uniform level, which is 0.3 solar. What we found here is that in the center, we have a sort of flattening, and I won't go too much into detail here, but just remember that this peak is there. This is a logarithm scale, by the way. So as I told you, we were not really impressed by this because we thought that this basically comes from type 1a supernova in the core of these clusters when you have these red and dead big galaxies in the core. But if this is true, then we wouldn't, we suppose that we shouldn't see that with other elements. For example, if you look at oxygen or silicon, which mainly come from core collapse supernovae, so from massive stars, so from those big blue stars, which are not in galaxy clusters, we thought that we should not see that. We should see instead something that is much more flat here or something like that. But when we look actually at all these other elements here, we see that they are all remarkably consistent with iron. So they all show this central peak here. So no matter if it's oxygen, silicon, sulfur, but all these elements coming from core collapse supernovae, so from massive stars. In other words, what you can say is that the relative contribution of type 1a versus core collapse supernovae in the ICM is uniform. So this just shows you like the fraction of type 1a over the total number of supernovae. So there's the plot, the value I showed you previously from these plots when you want to fit models of type 1a and core collapse versus observation. Then we just did that for different radii, and you can see that this is very, very stable, no matter which model you assume here. So this is true in the core. There's also this very nice paper, actually, by Cemile Ezer, which shows that this also holds if you go very far away from the core. If you look at the outskirts, you also have the same. So it really seems that you have no difference between, in terms of chemical composition, also from the core to the outskirts. So type 1a and core collapse supernovae have enriched everything uniformly. Okay, all right, I'm just going to spend a few seconds to explain a little bit the project I'm working on now, which is, so now we just would like to do the same for the elliptical galaxy NGC 1404, which is quite interesting because it's just entering into the Fornax cluster. And so it's not accreting any more gas. It might just be ejecting more gas here by ram pressure stripping, as you can see here. And it's quite interesting to look at this galaxy in terms of metals. So we have a few preliminary results here. So for example, an iron peak that we find also in this elliptical galaxy. And also, if you just look at the silicon over iron ratio or magnesium over iron ratio, you see that for magnesium over iron, at least in the center, is quite flat. These measurements are a bit more difficult to interpret. I think they are a bit less reliable. It's also quite interesting to note that unlike all the other previous results, we seem to have a bump here from silicon over iron here. And this is still a bit difficult to interpret. I won't go too much into details, but yeah, this is still under investigation anyway. All right, so if I just summarize now what we have, our main results are that the central iron abundance is similar for clusters, groups, and ellipticals. But remember that clusters form from groups, which form themselves from elliptical galaxies, right? So if we find a similar level of enrichments in all these different steps of formation, this means that probably the enrichment happened really early on, which again is, well, it's very much in line with what we found in the outskirts, like with simulations showing that black holes should eject metals very early in the history of galaxies and clusters. The second point, and this one is very, very surprising in my opinion, is that the chemical composition of the ICM is very similar to what we have in our solar neighborhood. And there's no reason for that, right? Because our Milky Way has a lot of massive stars, and it has a lot of successive episodes of star formation, etc., etc. While in galaxy clusters, we have something very different, right? We have these red-ended galaxies with almost no massive stars anymore, so no core collapse, supernovae anymore, so we shouldn't see as much oxygen as we would see in our sun. So how could that be? Well, one explanation is that this is perhaps not a coincidence, and perhaps this is just that you have this sort of uniform chemical composition that happened, again, very early on. So all these metals were really well mixed, and then somehow this has just cooled in the Milky Way and formed the solar system as we see it today. And finally, as I explained you also, like you don't find any difference between type 1a and supernovae enrichments, so between oxygen over iron, etc., from the core to the outskirts. So you both have this central peak for iron, for oxygen, etc. And if you go outside of the core, you have also these same ratios very far away. And again, this is very much in line with the fact that the metals were enriched quite early on, and that actually the central peaks that we find in the core do not come from a delayed episode of delayed enrichment by type 1a from the BCG. Perhaps it comes from something else. Perhaps it comes from much earlier in the cluster history. So again, all this really converge towards this view that central, well, not only the enrichment in the outskirts, but also the central enrichment happened really early on. All right, so now, of course, what we would like to do is that we would like to probe directly this chemical evolution, right? We really would like to look at higher and higher redshift and see whether indeed at redshift 2 or even 1, why not, whether we would see such an evolution or not. The problem is that this is not easy to do, and you can see here that we have a lot of statistical uncertainties here on these measurements. Why? Well, simply because we don't have enough photons for that. And that's why the future missions will be very, very important to get better measurements here and push these plots not only to redshift 1 or 1.2, but really to push it to redshift 2, for example, or even more. So, which is why I'm going to introduce now future missions. I hope I still have some time, Morad.
Yeah. You may go on.
Okay, cool. Thanks. I will just take 2-3 more minutes then, hopefully.
Okay.
So, yeah, the first new mission coming now, and that will come quite fast because it's in 2023, it's CRISM. So CRISM is just basically a reflight of Hitomi. And that's really great because Hitomi already has demonstrated how great your results will be if you can just improve your spectral resolution. And so, for example, on this simulation, again, you can see like all these beautiful lines that we will be able to resolve with Hitomi. And for example, we will be able to resolve new elements as well. So for example, sodium or aluminum, which we cannot see yet in the with our moderate resolution spectra. But here, if we are able to measure the abundances of sodium and aluminum, that will be very important because these elements are very sensitive to the initial metallicities of core collapse progenitors. So they will really help us to better understand the history of the bulk of core collapse supernovae in the universe. And similarly, we will have a much better constraint on manganese and nickel. And these ratios are very important to understand how type 1a exploded, and even before their explosion, what type 1a were. Whether they were like this these white dwarfs that just collided, or whether it's just one white dwarf that has progressively accreted material from a main sequence star. So this is for Crescent, but then the next game changer for sure would definitely be Athena. So Athena has basically the advantage of Crescent, which has like also this very nice microcalorimeter instrument, which means that you can also resolve the lines very, very well in your spectra. But in addition, Athena will be much more sensitive. As you can see here, it's like a factor of 10 compared to XM Newton, and even a factor of 100 compared to Crescent. And so the big change is that now we will really be able to probe these early clusters at redshift 1, for example. So this is just a simulation on how they will look like. And here again, you can see a simulated spectrum of such a cluster at redshift 1 from now. And you can see how we will see how we basically see these clusters now, for example, with XM Newton or with Chandra or even with Crescent, how we'll see them. And you see that the difference is extraordinary, right? And that now we will be able to probe not only iron at high redshift, but also all the other elements like oxygen, neon, magnesium, silicon, etc. So thanks to Athena, which will be launched, well, here I say 2032, but actually it's 2034, I think. You will really be able to push forward our knowledge on this history of the enrichment. Another slide I quickly would like to show you. This also comes from simulations that we have done recently, where we have just like simulated galaxy clusters with some sort of chemical enrichment, and then we try to observe it with mock observations of Athena to see how it would look like. And basically, the histograms just show the metals that we put as an input in our simulations, and the observations here in black just show what are the abundances that we get back. And you see that this is again very, very consistent here. And on this plot, what you have here is that you have basically these type 1a plus core collapse models fitted with all these ratios. So this exercise I showed you before. But of course, you can do that for many, many, many models. And what I show on this plot is that the black arrow here shows the input model. So the input yields from the literature that we took, and all the other data points here show basically all the other combinations of models you can imagine. And so this exercise basically shows that Athena will be able really, really well to constrain well and to isolate which model is basically the best to refavor type 1a and core collapse supernova physics in the universe. So, which is why Athena will be extremely promising. Of course, for that, the improvements of nucleosynthesis yields, as I explained you, so that I explained you, they are not really well reproducing the ratios right now, and improvement on atomic codes. So just having new specs version, for example, or new X spec version will be very important. So both these improvements will really be required to push forward our knowledge on the metals here. Very, very quickly, this shows you like how the uncertainties we still have on X spec versus specs. So the two spectral codes that we have right now, and you see that differences are still on the order sometimes of 10, 20, 30%. So there's still some work to be done, but we hope to be able to do that really soon. Thanks to Crescent, that will really help us to better understand all these lines, all these atomic transitions. All right. So in conclusion, just a very basic take-home message. The link between supermassive black holes, supernovae, and galaxy clusters is metals. Why? Because metals are found in galaxy clusters, so metals coming from type 1a and core collapse supernovae, and supermassive black holes inside the galaxies of these clusters really helped to push these metals and to mix them and to store them everywhere in the cluster volume. So these metals are found out to the largest scales of the universe. The chemical enrichment is remarkably uniform in many aspects. It can be on system mass, it can be on the distance, on the radial distance, on the ratios between I don't know, oxygen versus iron, silicon versus iron, etc. And so all this points towards an early enrichment that happened more than 10 giga-year ago. And as I told you, this really comes from AGN feedback. So here's really the link between these three aspects. And of course, now we want to probe direct evidence for this, this very early evolution of metal enrichment in the universe, but this will really come with future missions like CRISM and Athena. And I will stop here. So thank you very, very much for your attention, and I'll be really happy to take any questions.
Thank you, Francois. And I guess we may continue with the questions or any comments. Ömer, if you are following, maybe they will raise their hands for the question.
Participants, if you want any kind of asking question, please raise hand from the downside bar.
The Ömer will control the microphone. I want to ask a question for myself.
Sure.
And you said in the CHEERS project, like we know that in ellipticals and groups and clusters, we have the same similar iron abundance distribution. Is that the motivation to combine? Because in CHEERS project, you have 44 samples. It's a combination of individual galaxies, groups, and clusters. So what was the initial motivation to combine these different types of objects, you know? So seeing the iron distribution being similar is the motivation to combine?
Yeah, that's a good question. Maybe I can...
Do you understand what I'm saying?
Yeah, I totally understand what you're saying. I'm just trying to go back to the CHEERS. Yes. Because
like from the beginning, you might not be sure with ellipticals and clusters to have the same feature. So it's kind of like the assumption that because combining, I mean, putting them all into the same sample is...
Yes, yes, indeed. So can you see my screen right now or?
Not now.
Oh, okay, let me see. Maybe somehow it has stopped sharing. Okay, I'm just going to share my screen again. All right, I guess now you should be seeing it.
The sample is dominated with clusters or?
So yes, so in the sample, basically there's, if I remember correctly, there's 23 clusters and 21 groups / ellipticals. So first of all, I have to say this sample is not representative of anything. We didn't try to make this sample to a sort of representative systems of the nearby universe or whatever. The main criterion here is shown here actually. It's the fact that the oxygen 8 line in RGS, so in this RGS detector, is detected with more than 5 sigma. And the reason why it was this, because we know that if this iron line, if this oxygen line is well detected, then we know that the other metals will be detected. And so we really wanted to take the systems in the nearby universe for which the metallicities and the abundances could be the best measured, the more accurately measured, no matter whether they're clusters, groups, ellipticals, etc. So
I understand, of course, with each sample, I will see some lines, but you know, different ratios maybe. That's why I try.
Yeah, exactly. So
because
initially, yeah, exactly. So initially it was not. it was not meant for comparing between both, actually. So there was actually, so before the chair sample, there was a previous paper by Deplat in 2007, where it showed that at least for clusters, the difference in ratios were not so different. So basically the assumption was that for clusters, it would basically stay the same. Now we were still not really sure for groups and ellipticals, but asking for more data for that was actually also one of the reasons to basically compare. And if you see that the ratios don't change, then you are basically allowed to stack them all together, you know, to have more, to have more statistics. So that was a bit the background behind.
Thank you. We have a question from Kıyami.
Kıyami'den başlıyorum.
Tamam. Sonra da Özgür Hocam bekliyor sanırım.
Kıyami Bey buyurun.
Teşekkürler. Good evening. Thank you very much for the nice talk. I have two little questions. The first one is, do you think that different wavelength observations of member galaxies can give clues about their enrichment of their environment plasma for the ICM? The second one is, the atomic databases are improving. Our spectral resolution will improve with the new missions. In this manner, what is our current status of representational plasma, the plasma models, for example, multi-temperature models? Are they also improving, or they are enough for us? What's your opinion about that? Thank you.
Okay. Right. Thank you very much. I will answer for the first question. So the first question was about this multi-wavelength approach. That's a very good point, actually. And to be honest, I'm not a specialist of other wavelength, so I couldn't tell you exactly what we can do. But I'm starting to probe, to dig a bit into the topic, and it seems that you can still do a lot of interesting things. For example, what you can do is that you can look at high redshift galaxies, which have a sort of circumgalactic medium, which does not shine in X-rays, but there's still some gaseous halo there, which is much cooler. And if you happen to have like a background quasar really far away, that just pierces through this circumgalactic medium, if you look, for example, in optical or in infrared, you should see like the lines in absorption, so not in emission, but in absorption of this gas. And then if you know the ionization status of this gas quite well, then you will be able to measure some chemical abundances there. And this could be, for example, interesting because you could compare let's say the ratios that you have there for these galaxies at higher redshift, so whether in the cluster or not in the cluster, to what we find today in this hot gaseous halo. So this is one thing you can do. Another thing you can do is, if you like multi-wavelength approach, is to look even at nearby redshifts. You can look at the stellar abundances of clusters. So you can look, for example, at so the abundances of the stars you have with SDSS or stuff like that in a cluster, and you can compare the ratios of these abundances with the ratios of abundances you have in the gas. And that was like a very, so if you're interested, there's a nice discussion on that in the paper by Simunescu et al. And they show actually that in stars, the alpha over iron ratio, so the oxygen over iron or silicon over iron, is usually much higher than in clusters. In the intracluster medium, so in this hot gas. And that's very interesting because if you don't have this same ratio, it means that somehow this is kind of different, right? Like the stars that you have today is very difficult to imagine that somehow they can enrich the intracluster medium and provide a different ratios that you have now. So this might be one more clue towards the fact that the stellar population now has very little to do with the enrichment of the gas. So this is something interesting that can be probed. And now to answer your second question, so this was about the models and the model improvement. That's a very, very difficult question, actually. I don't really know I don't really know like what is the best strategies to improve these models. What is sure is that we have to improve them at different levels. First, if you just look at only a single plasma model, so single temperature plasma model, it's important that that you have an agreement between the two main ones, so X-spec and specs. That's certainly important. And then you have, so you mentioned in your second question, you mentioned this this multi-temperature structure. So I didn't really discuss that here, but this is indeed very, very important to model the gas with multi-temperature structure. So what is exactly the temperature structure of the gas, whether it's like 2-3 different temperatures or sort of continuous distribution of temperatures, this is very difficult to say. Some optimistic people believe that with CRISM, you will be able to say more about that because you will be really able to see a lot of key lines. And sometimes line ratios can tell you something useful about the temperature you have. And if you have different line ratios, then you can say, oh, well, I see that there's some gas which is at, I don't know, like 2 kV, some gas at 5 kV, etc. And then you can hope to get a sort of rough distribution. But some more pessimistic people, I would say, or maybe more realistic people would say that even though this will be very, very difficult to do, even if you have a very, very good spectral resolution. So here we don't really know. I still want to be optimistic, and I still want to believe that with CRISM we will be able to say more about this. But yeah, only the future will tell us.
Thank you very much.
Thank you. Okay, Özgür, do you have a question or accidentally?
Özgür Bey, size söz verdik.
Hello. Do you hear me?
Yes, we can hear you.
Yes.
Okay. First of all, thank you very much for this nice talk, and thanks for our institute to organize such nice talks. I am, as a mathematician, I try to catch some new informations, and it's very nice. I want to ask the mathematical background. I see models and I see graphs in this and some simulations. What kind of equations do you use in these models? What kind of mathematical background exists? Maybe for a research subject, what can I understand, or what should I study in this field? Is there research topics related to mathematicians? I am sure there are, but could you explain?
Yes, thank you very much for your question. Yeah, actually, it's the first time that I hear this question, and that's very, very interesting. So I might disappoint you a little bit in the sense that for at least for the research I've presented here, which is mostly observational, yeah, you might have very disappointing mathematics in the sense that, for example, when I show that we fit models, we fit models on observations, this is just done with a chi-square approach, for example. So this is very, very simple. You just have a few free parameters, and it's basically a standard fit. So there's nothing really, really difficult there. Okay, maybe we can go to a slightly upper level, which is about fitting of spectra. So if you fit spectra, usually it's also like, in principle, it's also like a very easy chi-square approach. However, it has been shown that sometimes you have spectra which have not a high number of counts. And when this is the case, you might actually create some mathematical biases if you just fit your spectra with the chi-square approach, simply because there will be some spectral bins which will have 0 counts. And that way you will just introduce a 0 in your denominator somewhere for your chi-square value. So this is not good. Then what you can do instead is use what is called the C statistics. So it's a sort of variant of the cache statistics that was implemented, I think, in the late 70s. So yeah, if you're interested in this, of course I can give you a paper discussing this more in details. Now, if you're really motivated about, complex and rich equations, etc., I think the best to search for is really in simulations, because in simulations, these are like very, very important, of course, to complement to observations. Also, as I showed, because if you look at the cluster outskirts, it's good to have an agreement between observations and simulations. And in simulations, then people really try to simulate cosmological volumes. So not only in chemical enrichment, but in thermodynamics, etc., etc. And for that, they have to implement a lot of equations, like equations of hydrodynamics, for example. Also a good implementation of all the chemical enrichments, diffusion processes as well. That might be very important in physics. And depending on the approach you use for the simulations, so it's either the Eulerian approach or the Lagrangian approach. So if you just want to focus on particles or just on the fluid, like fluid movement at a definite scale, you might get different answers. And that's very important, mathematically speaking, to understand what is the source of these differences here. So I'm not an expert in that, I have to say, because I'm much more observational. But yeah, there are a lot of colleagues who are doing simulations and who are struggling with these mathematical approaches. So yeah.
Okay, maybe these notes, these points, you can consider some fitting curves, or these considering like datas, these points in the galaxies, these stars, these lights, and then you can model in some ways, maybe some fitting curves, maybe some you say wavelengths, maybe about the waves you can give some model, and then the behavior of these waves, maybe it makes sense in physical means. So I hope in the future.
Thank you.
Okay, thank you.
Francois, because around 100 attendees, listeners we had, and it's mostly combined with engineers, not pure physics, mathematicians, statistical people, and engineers. So the things that we talk here opens some other ideas and triggering some new motivations.
Which is great, actually.
Yeah.
Very nice to have this
multidisciplinary
approach.
Collaborations. Do we have any more, Ömer, questions?
So it seems there is no hand.
Okay. I want to ask another thing. For the Perseus result with the Hitomi, you said it was also confirmed that very flat till the outskirts, right? Like manganese and nitrogen. And you said also with the spec 2, and you improved the version with spec 3, which was fitting more like the less manganese and nitrogen, or the ratios were fitting. So what was the improvement with these two versions? You added some additional origin for those manganese and nitrogen?
I think I can show you. I don't know if you can see my screen, because I have...
Yes, RGS, Hydra.
Okay, perfect. I think I have... that's a very, very good question. And I think I have... Yeah, this slide will probably explain you. This one, or... Yes, perfect, this one. I will first take the case of nickel, because I think nickel is the most important here. You have really a huge difference. So specs 2 tends to overestimate the nickel over iron ratio. And what happened was actually discovered thanks to Hitomi. And actually, if you look at this plot here on the bottom right, you see, so in the nickel bands, so well, basically in the spectral band where nickel ions are picked here, you can see the difference between specs 2 and specs 3. So in the upper panel, you have only the iron ions, and in the lower panel, you have the nickel ions. So you can see there are quite differences, but if you look at the lower panel, for example, you see that lines are a little bit different in terms of energy, in terms of equivalent width. However, you can imagine that the total flux here would be kind of comparable. Now, if you look at the iron ions, this is a completely different story. because SPEX3, which was implemented after Hitomi actually, found that there are a lot of iron lines which are actually in these nickel bands. And you can resolve these lines with Hitomi, but you cannot resolve them with XM Newton. And so what happened with SPEX version 2 is that, well, so basically it was just trying to fit this XM Newton data shown here in red, so just a big bump. And if these lines are not incorporated, of course, your predicted flux of this entire band will be lower than what your data shows. And so by compensation, to compensate, the model always wanted to fit more nickel to really fit this bump quite well. So that's basically what happened for nickel.
So can we use SPEC3 for XMM, or it's overdue for XMM?
Sorry, say it again.
Can I use SPEC3 for the XMM
yes.
data?
Yes. So if I just go back to this slide, let me show you. Yes. So this is this one summarizes everything. So the all SPEX2 results for XMM are shown here in the yellow and white data points. And so indeed, you see that nickel was clearly too high. And in blue, what we try to do is to take exactly the same data from the chair sample, so from XM Newton,
yes,
and just refit them with SPEC3. And even if we have a lower resolution than Hitomi, you see that, for example, for nickel, we have something that is very
yes, with the PERSYS result,
which is very reassuring, actually. Now, for manganese, I can tell you, I don't exactly remember why we found
larger
a
error bars,
higher value here. I can just explain you like the very large value we have here, which is simply that for MOS1, we had something very consistent. For MOS, so MOS1 and MOS2, was something very consistent here. And for PN, so this other detector on XM Newton, we had something unusually high, actually.
Okay.
And, you know, when I look at this, I would be really tempted to say that MOS1 is right and PN is wrong. But back then in that paper, we had no further evidence for that. So we still wanted to be very, very conservative and just take very...
Yeah, within the error bars, it's consistent anyway.
Yeah. But I would assume that's for manganese also, the fact that you implement more lines actually will basically make the flux of your line naturally higher, of your unresolved line from XM. And that's probably why you would not overestimate these amounts anymore.
Okay, thank you very much. We have a question from chat. Okay, but it sounds like, okay, from Sona, what kind of physical forces affected to the process of creation of elements or creation of particles like electrons, protons, and neutrons? And it sounds like a question for whole other seminar title.
That's a very...
Do you have any words on but
yeah, so it's basically, so I'm really not expert in that, but what I could say is that the forces that are really important for the creation of metals are, of course, the nuclear forces that will really help to build, for example, an atom of helium out of an atom of hydrogen, and then to build an atom of carbon out of helium, etc. So this really has to do with nuclear forces. Now I have to say I'm not an expert in that.
Yes.
But for example, people who are modeling, we'll try to find, so people who are trying to model like nucleosynthesis models. So for example, if I just go back, here, for example, all these people who are trying to model these supernova explosions, then they really incorporate this nuclear physics in their codes, and eventually they can just predict these nuclear synthesis yields. But something that I can also say is that you have different research groups doing that, and even for the same assumption, so let's say, for example, initial metallicity of 0 and a salpeter IMF, or just a given mass, they still find differences. And that's probably because even the physics there is not exactly, it's not exactly well understood. For example, some elements are created because you have a neutron capture, because you have high density, etc., or electron capture to create a neutron from a proton and an electron. And but this is still a bit unclear apparently. So there are still some theoretical discussions going on there.
Yeah, because these initial mass functions will decide your initial budget of the, let's say, the energy or the forces that will start the whole story. So that will decide the end,
yes,
the picture
yeah,
that you will have at the end.
Exactly. So the initial mass function actually will just define your initial masses, and each mass will probably, so with gravity, you will probably have different processes at play in the calculations of these yields, indeed, yeah.
Okay, any more questions or comments? I guess we are all clear. Ömer, do we have any? No, right? Chats? Okay, I guess we completed more than 1 hour, 1 hour and 20 minutes. Again, I would like to thank on behalf of our university and the institute to Francois for taking his time from his busy schedule and giving us this beautiful, mind-blowing seminar. Thank you, Francois, and hope to host you in our university physically as well.
Thank you very much for inviting me to this seminar. I really enjoyed it myself too. So,
okay, thank you.
The questions were really interesting as well.
Okay, I hope to meet you next week. Grad Talks to all participants. Good evening, everyone. Thank you.
Thank you. Bye-bye.
Thank you, Francois. Bye.